Our last keynote address is by Professor Dr. Siddhartha Mishra. He is Chair Professor of Applied Mathematics at ETH Zurich. He is also the Director of Computational Science Zurich. He is a core faculty member of the ETH AI Center, and he is a steering committee member of the Swiss National AI Institute. His research interests lie in the field of numerical analysis, scientific computing, and machine learning, with applications to different fields of science and engineering, ranging from fluid dynamics to biology. He is an elected fellow of the European Academy of Sciences, and he is a recipient of many awards and honors: the Collatz Prize of ICIAM, the Dackwitz Prize of SIAM, and many more. We are honored to have Professor Dr. Siddhartha Mishra with us. Moving over to him.
Okay, so first of all, thank you very much, Shashi and the organizers for inviting me. I couldn't come this time either. It's sort of towards the end of my semester, so there are a lot of exams and so on. Okay, so let me get started. I'm going to talk about data-driven simulations in physics and the role that AI plays in it. And the obvious starting point is, so if we are talking about data-driven simulations, what is the current paradigm for simulations in physics, right? And this is something that you have been exposed to repeatedly. So we all know that the starting point of any simulation is to have a mathematical model, and in the realm of physics at least, partial differential equations or PDEs, these are sort of the dominant paradigm, because we know that they are the language of nature. The model sort of physical phenomena at all kinds of scales, so starting from subatomic particles, electrons for instance, modeled by the Schrodinger's equation, to more or less at cosmological scales, like the collision of two black holes which sends out gravitational waves, in turn modeled by the Einstein equations, and everything in between. So there is this immense diversity of physical processes as well as this very wide range of spatiotemporal scales, and what is sort of unifying them is a common
recording in progress,
a mathematical description which is provided by PDEs. So that's the first step. But we all know that PDEs, you cannot write down exact solutions, analytical solutions. So we rely on numerical methods, and there are plenty of numerical methods to choose from. Find difference, find elements, spectral methods, find volume, and so on. And this is a very, very successful paradigm. So a lot of simulation happens, including in my own lab, for instance, where we could simulate things like core collapse of supernovas, waves in the sun, clouds, tsunamis, industrial processes, flows past obstacles, rockets, and so on. And many of these problems very successfully. So this is a very, very successful paradigm, right? Then the question that arises is, why do we look for alternatives then? What's the catch? What's the caveat? And again, I think some of you already know them, perhaps all of you know the answer. So there are two reasons I believe that the current paradigm has weaknesses. The first is that of cost, and this is very apparent. You'll see several examples of this. But just to give you a sense of the cost that we're talking about, so if you have a fluid flow, in this case just in a box, periodic boundary conditions for 3D, Navier-Stokes equation, a direct numerical simulation as we call it, and then you can see that this is the initial condition, this is how the flow looks like after a while, and this is done at a very high resolution, 1000 cubed, so a billion degrees of freedom, or more than a billion degrees of freedom per time step. And we have a highly optimized GPU core. We run it on a supercomputer, the most powerful one that we can get our hands on, and still this is an expensive simulation. It takes about 100 hours per simulation because we did it on a GPU. On a CPU, this would be 50 times, 45 times more. But that's not the main point. The main point is that a single simulation in this context is fairly useless, because when you change the initial conditions ever so slightly, you see that the solution changes quite a lot. So this is a problem which is ripe for uncertainty quantification. You have to do multiple simulations, and then what happens is that this cost gets multiplied by a factor of 100, for instance. 100,000 node hours, and this is expensive, right? If you go to the market, it's about $8 node hour, so this becomes very, very expensive. So, and you can see that there are many, many problems, design, control, optimization, inverse problems, uncertainty quantification, where the PDE solver has to be called again and again and again. And these are exactly the kind of problems where you cannot, with the current methodology, with the current framework, proceed much. And you'll see many examples of that. But that to me is only one part of the story. The real sort of challenge in some sense is we make an assumption that we know the physics exactly, right? So just let's take the Earth system. So in the Earth system, we know that the flows in the atmosphere and the ocean, these are modeled by some variants of the Navier-Stokes equation. We also know that radiation is modeled by radiative transfer equations. So there the physics is sort of tight, right? On the other hand, there are many processes here. For instance, you can think of the land, you can think of vegetation, aerosols. There are many different elements to the Earth system where you cannot sit down and write the equations. You cannot sit down and write the ODEs or the PDEs that govern them, and then people end up fitting a lot of parameters, and this is not good enough. So in some sense, a lot of physics and real world problems is actually missing. And what it leads to is what is called a sim to real gap. This is a terminology from robotics, but essentially what happens is that your best simulation, even if you have a perfect simulation of your system, you will still end up with errors, and these errors don't go away because these are modeling errors, right? And this is, in the real world, this is I think in some sense the biggest challenge. So either you have issue of speed, things are slow, or you have an issue of accuracy, that things are just too inaccurate, there are modeling errors. So what we haven't sort of exploited in this entire discussion is the role of data, but the whole conference has been about that. The question is, can we sort of leverage data together with the physics to learn the solutions of these physical systems which are modeled by PDEs? And that would be my objective for the rest of the talk. So now when we talk about learning the solution of the PDEs, then we have to be much more precise, mathematically precise, and we should just double back a little and understand what that entails. So if you think of different examples of PDEs, so here is a classic example, elliptic PDE, Poisson-Darcy type equation, and then what the input to the system is given by the forcing term F and by the coefficient A, and output is given by the solution. So this, for instance, could be your material property, it could be your conductivity, and this could be a voltage or a temperature or something like that. Similarly, for initial value problems, time-dependent problems, you want the mapping that takes the system. It as an input, it has the initial conditions, and as an output, it has a solution at a later time. So these are sort of the input-output relationships of these systems. And then the relationship or the mapping that relates them is given by what is called a solution operator, which takes an input and produces the PDE solution as its output, right? And these are essentially infinite dimensional objects because these are functions. So A and U are fields or functions. So this is essentially an infinite dimensional object. And when we want to learn the solution operator, because when you change the inputs, you get a different solution, and then you can sort of barrel through that. But then we set up some distribution, a probability measure on functions. This can be readily done. We sample from this distribution, and then we obtain a data set from which we are going to learn the solution operator. And this is the task. So the task is really to find an approximation of what is called a push forward measure. But remember that this is an essentially infinite dimensional problem. Now, how are we going to learn this object, this operator? So, of course, we are in the age of AI. The whole conference is about that. So, we are going to use the available technology that is out there, particularly neural networks, which are the most powerful paradigms for learning tasks, learning representations, for instance. But then almost immediately we have a problem, because neural networks, these are essentially mappings of whatever type, whether they're MLPs or CNNs or transformers. These are essentially mappings which take a finite dimensional, could be a very large dimensional input, and they produce a finite dimensional, potentially very large dimensional output. But if you recall in the last slide, what I told you is that our problem is essentially infinite dimensional, because the inputs and outputs are functions. So what we have to do is to link this world with this world, the infinite to the finite. So either we can project from infinite to finite, or we can lift from finite to infinite. These are the main possibilities. So one possibility, they all end up being equivalent in some sense, was the idea of neural operators, which was first formalized at least by Nick Kovacsky and his collaborators at Caltech a few years ago. And the idea is that just like neural networks are finite dimensional learning paradigms or learning approaches, why don't we generalize them to infinite dimensions? So we keep the same sort of a block or layer structure, compositional structure, as in neural networks, but unlike in neural networks where the input is a vector, here the input is going to be a function. So this input function is given by v, so it can be evaluated at different points in your domain, and this is your input. So as soon as the input becomes a function, this bias vector has to be replaced by what is called a bias function. That's obvious. The non-trivial operation is this matrix vector multiply. So this is the core of a neural network, the weight matrix multiplying with the input vector. And the elementary analysis, elementary function analysis tells us that a matrix vector multiplier's infinite dimensional analog is this kernel integral operator. So you take a kernel, you throw it against, multiply it against your input, and then you integrate across the domain. And then we have the activation function. This is your nonlinearity, and this can be applied pointwise. This was the original proposal of Kovacsky et al. But we came in the scene some years later, and we said, no, this can also be a very general operator. It can be non-local operator. But now, so this is the paradigm. This is a straightforward extension of a infinite dimensional extension of neural networks. That's why they are called neural operators. But of course, the devil is in the details. Means you cannot. You have to implement this on a computer. You have to discretize these infinite dimensional objects. For instance, the integral, the non-locality, and so on. And there are different choices that one can make. So let me walk you through some of the choices. I'm sure you have seen some others in the conference. The first choice, the most canonical choice, is to use a convolutional kernel. So instead of having this general kernel here, we make it into a convolution or a translation invariant kernel rather. So that's because a lot of physics is translation invariant. So when you have a translation invariant kernel, you can do everything in the Fourier space. So the kernel integral operator here, which is a convolution, it becomes, or it can be instantiated in Fourier space. So what you do is you take a function, discretize it on the grid for instance, take its Fourier transform, apply a learnable matrix or Fourier multiplier, this is the learnable parameter here, take an inverse Fourier transform, come back to physical space, and then apply the nonlinearity pointwise. So this was the idea of what is called the Fourier neural operator. This is due to Zhongyi Li and his co-authors at Caltech. And this is, so remember that the convolution itself is non-local, but the activation function is going to be a local function, the nonlinearity. And this can be implemented in sort of log linear complexity on a Cartesian grid using FFT. But this is not the only choice. There are many choices. There are hundreds, perhaps thousands of choices now. But one choice that I would sort of advertise here is the choice made by us a couple of years ago. And this is to use convolutions, still convolutions, but no longer in Fourier space, but rather local convolutions in physical space. So there is no issue of computational complexity. The main difference is not in the convolution, but it rather is in the nonlinearity. And the reason for that is, remember that here the nonlinearity is applied pointwise, right? So at every point you stick in the nonlinearity and then evaluate it. So what happens as a consequence is that if you take this function in range and then you apply the nonlinearity pointwise, this is ReLU. So pointwise this is good, it's just a positive part of the function. But when you look at it in Fourier space, which is an equivalent description of the function, what you see is that my original function was band limited. It was between -20 and 20 in Fourier frequencies. All the other modes were 0, but by applying the nonlinearity, what you do is that you introduce high frequencies that are not there in the data, right? So this is what is called aliasing in spectral methods, and we claimed in this paper that this led to errors. And we wanted to get rid of these errors or minimize them. So we said that instead one has to use the non-local activations. One has to grow the frequency space, work in the frequency space, and then apply the non-linearity, and this leads to what is called a convolutional neural operator. So now you have local convolutions but non-local activations. In principle, in practice, it is realized as a UNet, which is a multi-scale information processing vehicle, but this is just a detail. So these are the choices that are in front of us. and this leads to some measurable, let's say, differences between them. So for instance, this is Navier-Stokes. The initial condition is your input, your output is the solution at a later time. You can visualize it very nicely in vorticity, but the inputs and outputs and velocity space. And what we observe here are at a fixed resolution, but the whole point about neural operators is that you can evaluate this architecture at any resolution. So we train all our baselines, let's say, at the resolution of 64 squared, one particular resolution. We get a certain error which is relatively low, but then the point is that as you increase the resolution or decrease the resolution, your machine learning algorithm should be able to generalize. It should be able to understand that this is actually a function that we are inputting and not a particular discrete vector. It turns out that if you just use the convolutional neural network, you get very poor results, because as soon as you change the resolution, the errors just shoot up in both directions. FNO controls this quite a lot, so there is a small growth of error when you super resolve, more growth when you sub resolve, and that is purely due to aliasing. In the paper we explained that. But our architecture, which was designed to sort of confront this, to tackle this, is essentially does this seamlessly. So it's able to generalize very well across grids. And this is because underlying it is a key mathematical principle that whether you lift to infinite dimensions and then discretize, or you discretize first from infinite dimensions to finite dimensions, these objects should commute. And this is what is underlying that. But this is sort of an important detail. But remember that both these architectures, they were based on let's say convolutional kernels, right? Either in Fourier space and physical space. So essentially linear kernels. So remember that we have this kernel integral operator, and so far I showed you examples where the kernel is going to be linear. Now here is an example where the kernel is actually non-linear, because nothing prevents us from considering non-linear kernels. This is called what is called operator attention. This is the backbone behind transformers, which are famous due to LLMs, but in this context they can also be used. I mean, there's a particular choice of a non-linear kernel, non-local and non-linear kernel. I don't need to go into the details, but the main point is that it can be the same technology can be applied to this, and when we in practice, when we work with it, we use what are called vision transformers or swim transformers, so that the computational complexity is kept in control. This is just a generalization of finite volume methods, but I think I spoke about it last year, so I'm not going to belabor the point. So there are the message here is that there are different methods and they all fit into roughly the same framework. And as long as you evaluate them on 2D in Cartesian grids, they work seamlessly. They work very, very well. There are minor differences here and there. Some methods are better in one case, some methods are better in another case. But essentially in the last, I would say 3-4 years, most of the issues in 2D on Cartesian grids has been solved. But as you can imagine, this is not where engineering is. Engineering is about arbitrary domains, 2D, but increasingly in 3D. So here is an example. So what we have done very effectively in the community, not just in my lab, is to be able to resolve this situation where my inputs and outputs are on Cartesian grids. But in reality, even in 2D, if you flow past an airfoil, this is a supersonic flow, you can see that my inputs and outputs are on very complex point distributions, grid distributions. And in 3D, for instance, this is an actual grid on a race car. And this is, of course, much, much more complicated. So the question is, can we go from here, where we have very good solutions to learning the solution operator, to here, where the things are much more complex? And again, there are many, many architectures that are available today, but the one that I'm going to talk about now is something that just has been out of my lab. It was presented at NeurIPS in San Diego last week. It's called Geometry Aware Operator Transformer, and it's based on a very, very simple idea. So let me explain that to some extent. And just for completeness, what you can probably see on your screen is that my inputs are on this blue grid. So this is a grid that is flow past an airfoil, supersonic flow past an airfoil. So the idea is, of course, as in mathematics, what you do is that you take your unknown problem and somehow reduce it to a known problem, right? We know that we are very, very effective on Cartesian grids, were not that effective on this kind of unstructured arbitrary point distributions, the question that people ask themselves is, can we sort of transform the problem from Cartesian grids to, or from not unstructured grids or just point distributions to Cartesian grids? These are what are called latent grids, and you can do that. So this is what it does. This is what is called an encoder. So what you do is that you essentially take information that is on this blue grid and you sort of transform it into information on the red grid, right? So for each point on the red grid, you accumulate information from its neighbors by using essentially some sort of graph neural networks. These are not exactly graph neural networks, they're light graph neural networks, and you do it in a multi-scale manner. And what you end up is a bunch of tokens, or which are aware there is also some geometric information which is being provided here, all processed through MLPs. And then on the Cartesian grid, you have this tokens, so this pieces of information that you can use transformer. We prefer transformers. You'll see why. And then you make this processing. This you can also use CNO or FNO here, but let's say we take transformers. Then you have the processed output on a Cartesian grid, and you go back to the original grid. So you take any point on the original grid. Again, you do this in reverse. So you decode the information in reverse, and then you will have solution on this, right? So this is roughly the idea, that you take information which is on your very unstructured point cloud, you transform it into a Cartesian grid or any sort of reasonable latent grid, and then you process information there and come back. So it's sort of a natural idea, and this is sort of a good implementation, I would argue, for this. The advantage with our architecture, Keynote as it's called, or code, some people call it, is that it's very flexible. Now you can do all kinds of problems that you hitherto couldn't, right? So for instance, this is a transonic flow or a supersonic flow past airfoil. This is a supersonic flow past a spear or a ball in this particular case, and this is a problem in elasticity. All of this requires handling complex grids, and the architecture is able to do that. It's pretty accurate. It's pretty accurate. It's actually the most accurate here, but it's not just about accuracy, because we also have in the lab a completely graph neural network based architecture that is as accurate or comparable accuracy. But the main point where this architecture scores is that it is efficient. What does efficiency mean? So remember that now I could have a lot of input points and I could have a big model size. So for instance, in terms of the input points, as if I take only, I don't know, I can't see very well here, but if I just take 1,000 or 10,000 points, then the graph is very, you can process a lot of samples per second, so there's a training throughput. But as I keep on increasing my model size or my input size, then with other architectures what happens is that because of message passing, because of sort of sparse memory accesses, your throughput slows down. So at the end you are left with very little. So if the graphs change dramatically during training, then you are ending up in a situation where you cannot process large inputs, right? Whereas with this sort of mix of transformers and graphs, what you see is that the training throughput remains almost constant. So you can train a lot of samples, and it's the same with model size. For instance, with 100 million, you can only do one sample with a graph neural network. Here you can do about 60 or 70. So you can really train. So because it has this, let's say, computational ability, what you can do is you can now go to 3D. And this is the main point that I wanted to make. So here is an example. I think this is the best data set that is out there, prepared by Mohammed Al-Rafai at MIT. It's called DriverNet++. So you take different kinds of cars, hatchbacks, notchbacks, estate backs, and so on, passenger cars, and you do CFD across them, RAM simulations, and you want to predict things like pressure and wall shear stress and so on, CFD quantities, right? And there are approximately 8,000 cars, and if you just want to look at the surface, because that's what an engineer is interested in, there are about 500,000 nodes on the surface. So we implemented this architecture, and it does very, very well. In fact, at the full resolution, it was double as accurate as some of the other competing architectures. And the interesting thing is, when they designed the dataset, on an average for each car, it took them 400 node hours. So this is open form CPU, whereas with the evaluation here, it takes 1/3 a second. Right? So this is the main advantage of it. And this has become sort of a competition. It's called Car Bench, and these are some latest results from about a week ago. Because and what it tells us is that unless until you are able to train at the full resolution. So, for instance, let's take UPT. This is from my friends in Austria. What they do is that when you train it on let's say on a low resolution grade, you get very good errors. But as soon as you test it on high resolution, it doesn't work that well. But with our architecture, we can directly train at a high resolution. So at the moment, we are able to beat the best by a factor of 2. So this is the latest results. So you can really solve industrial scale 3D problems. You can up the ante. So this is another data set, which is again CFD passed cars, designed by Neil Ashton, who is now at NVIDIA. So Neil did is that he took similar kind of cars, the shapes, but instead of using a RAN simulation, this was an LES, a much more accurate simulation. So just to understand the scale of the problem, so instead of just having 500,000 points, which is already a lot, right, on the surface, this one has 9 million points. So you really need an architecture to be able to deal with this explosion in complexity, and again, our architecture was able to do it quite well. There's much less benchmarking for this particular one. But the main point is that this one, it took 60,000 node hours for Neil to generate a single sample on an average. Whereas with all the technology that goes in, it's about 10 seconds for the surrogate that we have. So this really shows the power of some of these machine learning models now. You can do a full aircraft, simulation past a full aircraft. This is from DLR, Philip Beckemeyer, the data set, and then we ran code, and I think it's the only one that can again do it on the full resolution, and it does a pretty good job. So that the point that I'm trying to make is that this is very new, not just in my lab, but again in the community. Like in the last 6 to 8 months, I would say, people have been able to scale up from just 2D sort of academic benchmarks to really industrial scale benchmarks. So this has been sort of an eye-opening discovery in some sense. But can we sort of push further? Can we go even more realistic? So here is an example, because what you saw so far are problems which are essentially monoscale, and as soon as problems are multi-scale, things are difficult, right? So here is an example. Again, 3D, now it's not, geometry is not an issue, because that was addressed in the last lecture, and in the last slide. So instead what we do here is just 3-dimensional fluid flow in a box. So this is the Taylor Green vortex. So this is the simulation with the spectral viscosity method. And here is what a neural operator, and no neural operator does better than this, right? So it's a combination of convolutions and FNOs, and this is what it gives. So immediately you see two things. First, all the fine information that is there is completely washed away, so you only get the large scales, nothing else, right? Second thing that you see is that the variation, because if you change the initial conditions ever so slightly, this is a chaotic system, you have big changes in the solution, and this is not at all captured. So there is a regression to the mean, and it is independent of the architecture that you have in mind. And this can be explained, so we have some theory to explain this. It's so easy that I can even do some math here and try to explain it to you. So essentially it arises, now neural networks are in some sense magical quantities, because they are universal approximators. So they can approximate any map, right, as long as it's continuous, for instance, or measurable even. But the point of our neural operators are the same sort of properties. But the point is, in the end, we are not just working with some random neural networks which have this expressivity. We have to train them, right? And we train them through gradient descent. So it means that the gradients have to be nicely behaved. And this is why people say that neural networks are working at the edge of chaos. That they're bounded gradients. Gradients are not small, they're not super large, they're bounded gradients. But when your ground truth itself is having very, very badly behaved gradients, remember that this is a very sensitive problem. Small changes, large variation, right? So this means that the gradients are very large, then neural networks struggle. How do they struggle? So let me just explain these two lines of math here. So S is your ground truth, right? So this I give a base state. For instance, this could be the base state, and then I make some perturbations, right? And then the ground truth, this does not reduce to the base state because these are very, very different from each other. But in a neural network, when you make these tiny little perturbations, you collapse to the base state because it cannot see these small perturbations, right? So because of that, what happens is that then you can break down this term into two terms. Essentially, it's an equality, it's a bias variance decomposition. One of these terms is variance. It essentially tells me it's independent of the neural network. Neural network is given by this tier here. So this term, it depends on the variance of your ground truth. And remember that here small perturbations lead to large variance. So you cannot train your neural network because this will always be a positive large term. And what happens here? The best you can do, it's a positive term. So you can make it 0. You can get it down to 0. And that will be by setting this to be the mean value. So this is a mathematical explanation based on a very realistic hypothesis which says why you observe what you observe, which is that neural networks, neural operators, whatever you call them, in this mode they will always collapse to the mean. So nothing can be done. So this is not nice in some sense, right, when you have these chaotic maps. But what we also know from some mathematical fluid dynamics is that it's sort of futile to learn this map itself, because just imagine trying to match every single well, every single vortex. This is simply impossible. What can be done instead is what is called statistical computation. So if you start with the probability distribution, which is somehow, these are samples from this probability distribution, you let them evolve, and then there will be some output probability distribution. So there is a way, there is some hope that we can go directly from here to here. So you have to learn conditional distributions, because I want to learn the distribution of solutions given the distribution of initial conditions, for instance. So this is the paradigm that one has to do. So we have to directly work with conditional distributions rather than with just push forwards of maps. How can we do that? Well, this is where machine learning excels. Means if you go to ChatGPT and you give it a prompt, a fox looking for its socks, it will give you a very nice picture. So the machine learning is sort of able, generative AI is able to do this kind of conditional sampling. And the way it does it these days is by using what are called diffusion models. So diffusion models are the most powerful distribution learners that are out there. There are other models like flow matching models and so on, but this is very attractive because what it does is, so remember that you have to sample from a distribution. So it takes samples from the distribution, you have some training samples, adds noise iteratively so that you end up with essentially normal distribution, right, white noise. And then at inference, you reverse the process. So you given a noisy distribution, given some inputs, you are going to iteratively take out the noise so that you generate a new sample from this distribution. So this noising and denoising process is the route through which a diffusion model works. And this noising and denoising both can be done through stochastic differential equations. This is the natural framework. So we took this, it is responsible for video diffusion, image diffusion and so on, and we sort of ported it to our application, to our use case. So this is a score-based diffusion model, it's called GenCFT, it's around from earlier this year. So what we do in GenCFT is that given a initial condition, for instance, given a clean sample, given something which is a training sample, we add noise in the forward process, and in the reverse process we solve this STE, reverse STE, so that we can recover, given this noise and given this initial condition, we can recover the solution at a later, and the time, of course, solution at a later time. But the key here is to use what is called a denoiser. A denoiser is another neural network whose role is very simple. It takes the condition, the initial condition, it takes the noisy sample, it takes the amount of noise, and then it produces a clean sample during the training process. So remember, it's still the same neural networks. Neural networks haven't changed, but the way in which we use them have changed. So earlier, we were trying to give some input and ask it to produce a chaotic output. This was impossible for a neural network. Now what we're doing is, we're giving it some noisy input and we're asking it to produce a clean output which is relatively close to it, because it just has to remove, even though the solution itself is complicated, its task is much simpler. And then this feeds into the SDE, where iteratively you sort of denoise till you get the solution. So it's a completely different route, and that's why it works. We can even mathematically prove in some simple cases that it will crudely approximate the conditional distribution. So this is a change of paradigm which enables this learning to happen. And in practice, you see that means it's almost impossible to distinguish. So let's look at this picture before. So this was the kinetic energy of the count root. This is the kinetic energy of a neural operator. And the same neural operator applied in the diffusion model, and you see how well the statistics or how well the sample quality is there. These are not meant to be exact. These are meant to be samples, right? And you see, for instance, the variance is beautifully captured, the spectral information is captured, and so on. So it essentially solves the problem that we were stuck on. And once you have it, once you have the principles, you can scale it up, right? You can go towards real world flows. So this is, for instance, a nozzle flow, very popular in engineering. This is a shock wave, shock turbulence interaction. This is an atmospheric flow. In all three cases, the method works. And again, the advantage is the power of the method is the time it takes, right? So even with the diffusion model, it takes about 3 seconds, whereas on the other hand, this one takes 15 or 14 hours. So it's really promising in that sense. Okay, so these are some success stories. I don't have a lot of time, I think, but I will try to wrap up by telling what's the caveat, right? What's the issue? So the main issue is, the good thing is, all these models scale with data. So as you increase the amount of data, you get better results. All the architectures that I showed you today. You can even prove that happens, essentially with the central limit theorem 0.5 as your upper bound, more or less, right? So what it turns out is that in practice, you need a lot of data, because the convergence is relatively slow, so you need anywhere between 1,000 and 10,000 training samples. So for instance, all these examples are between 3,000 and 8,000 samples. But the difficulty is we don't have access to that kind of data, except in some domains like weather or high energy physics. In general, in engineering, you don't have access to data. So you have to do something. You have to work with less amounts of data. And the way to go, in my opinion, is to use what are called foundation models, because LLMs have shown us that foundation models work. So what you do is that you train on different kinds of data distributions, and then you sort of fine-tune or adapt the model to a specific task. So that's roughly the idea. I think I spoke about it a little bit last year, but just to give you a very broad sense. So you have different PDEs which represent different kinds of physics. Each of them have different operators because you change the initial conditions, boundary conditions, and so on. And then during pre-training, you take a big neural network, and then you take some of these guys, pre-train them, and then at the time of deployment, you can either use a different PDE, and then you fine-tune it. So that's roughly the idea. And the reason is, there's no reason why they should work, because PDEs are very different from each other. There's no reason why learning on an elliptic PDE will help you with a parabolic PDE and so on. But last year at NeurIPS, we sort of demonstrated that this can be done. Other people have also done that more recently. So the idea is that, let me directly tell you what goes on. So we need a model, and the model is a transformer. It's a vision transformer. The details are not important here. And this was all done in 2D on a Cartesian grid, so not yet with all this 3D unstructured grid, multi-scales and so on. So the data came from Navier-Stokes and from the Euler equations in 2D. So these are the two standard equations of fluid dynamics. And we have quite a bit of data. So this is approximately 5 million image pairs, because we have a way to augment this data. And then different models were trained on it, pre-trained on it. So the largest model was about 650 million parameters. So it's a pretty big model. Not the biggest, but one of the biggest models around in this domain. And then what we did is that we fine-tuned, or we tried to demonstrate it at different downstream tasks, either with the same physics as during pre-training, or with completely different physics, right? So this, for instance, a Poisson equation has not been seen at all during pre-training, and we want to fine-tune it. The details are not important here, but let me just show you the results. And here there are many tasks, right? So I cannot show you pictures for every single task. So instead what we do is we compute two scores. One is the gain in efficiency. So if I take a baseline, for instance FNO, I compute the error with 1,000 FNO samples. So this in this case is 20%. It's just numbers. And then we see that how many less samples do we need to get 20% error. So in this case it was 40 samples. So then the sample efficiency gain is a factor of 50. So this is one thing. The other thing is again in accuracy. I fix 100 samples. I get, I don't know, okay, I'm sorry, it was not 20%, it was probably 2% error. So here is about 8% and this goes down to 1%. So this is again a factor of 8. And we did this across all these tasks. So on an average, we said that the sample efficiency gain is a factor of 50. So you can really use 20 samples to do what we are earlier doing on an average with 1,000 samples. Or if you have 100 samples, you gain a factor of 10. So this is a big success. There's some scaling and some comparisons, but this is somehow not the main point. This is at a small scale. It is still in 2D and so on. And just to give you an example of how this learning happens, you look at the Poisson equation. And here again means you have a very, very different problem. It is not fluid dynamics, right? This is not the initial conditions to solution at a later time mapping. It's really mapping between forcing term and the solution, which is diffusion, right? And it turns out that the model learns in a very interesting manner. So instead of averaging a fluid flow, even with one sample, what it does is that it's able to learn some element of diffusion. Within 16 samples, it has certainly learned diffusion, at least the basic mechanics of diffusion, if not the exact values. 128 samples, it really learns it. So essentially, we demonstrated that there was enough physics available in the fluid dynamics problems to learn about diffusion equation. So this was sort of the main point here. But as I said, it's a 2D sort of Cartesian grid model. We have 3D results. Other people also have 3D results now. But to incorporate everything else, unstructured grids, multiple physics, this kind of diffusion training for multi-scale problems, this is what we're doing at the moment. So perhaps in a few months, we'll have the next model, which will show it at a much larger scale. But the seed is there, the genesis is there. You literally can do this. So I think I have about 4 or 5 minutes, so I will finish by, I think, what is the most important element of my talk today in some sense, which is, okay, I showed you all these impressive results, also some of the challenges. The question is, when I talk to practitioners, CFD engineers or people in the industry, they say, how can we trust this, right? Means, what is the error? How do I know what the error is and so on? And this is a very, very hard problem. But here is some sort of an attempt to solve it. It's a very recent paper, a couple of months old. So if you remember, this is what we do in machine learning, right? We have a loss function, we have a ground truth, we have the prediction from a neural network, and we sort of weigh it against the probability density function. And this guy here is your generalization error. It's a mix of your training and validation errors, let's say. So our objective is to make this small, right? But what we really want is point-wise information. That a particular sample, how good are my results, right? So if you think of it, just imagine that there is no integral here. There is an integral and there is a math behind how to prevent that. So if you could just say that this is equally distributed, so I can remove the integral sign, it's anyway a probability measure, and then this is the picture that I get up to some error, right? Up to some error with some probability. So essentially my loss function scales with respect to my total generalization or training error, let's say, divided by the probability density function. So if it's high probability, then there will be low loss. If it's low probability, there will be high loss. And this is essentially what it tells. Now we can, of course, we can't divide like that, so you have to write down a log here. So this object is what is called a likelihood. And so essentially what this simple math tells us is that your error is highly correlated with the likelihood. And if you can somehow compute the likelihood, then we can get some handle or some estimate on the error. But how can we compute the likelihood, right? So it's a probability distribution. How do we compute that? It turns out that this is where diffusion models, the ones that I showed you before, these are optimal for doing it because these are distribution learners. So they can sample from a distribution. Again, I don't have time for the details. So what you do is that you take your model, means whatever model that you have, and on the same data, you do what is called an unconditional diffusion model. You train the diffusion model so that it is able to sample from the likelihood, and you combine these two to provide a score, a certificate. And this tells you several things. First of all, it tells you whether your testing sample is in or out of distribution, because this is the minimum that people want to know. That have I seen this in the training data before? Otherwise, it's out of distribution. Second, if possible, I want this certificate. I want to say where the error is, right? And this is, and what we demonstrated through various examples here is that you can actually show this. So let me give you a couple of examples. So this is for the wave equation, very simple problem. Initial data, solution at a later time. So in principle, you have no clue about what you're predicting, whether you're predicting. You don't have the ground truth, so you don't know whether your prediction is good enough or not, right? So what the certificate tells you is that in this case, the error is between 0.08 and 0.12, and indeed, and it's in distribution. So this was what the certificate told us, and here the ground truth is there. Here's another example. This one is not so well represented. So the certificate identifies that. It says that the error is larger. It's actually out of distribution. And again, the ground truth fits in very well. And these are not cherry-picked examples. You can see the whole spectrum out here. And maybe I even have some examples for Navier-Stokes. Again, similar picture. For instance, here, this is very out of distribution because it has been trained more or less on this distribution and deployed on this distribution. The certificate gives you a very large value. In this case, the error is actually a little less, but it's still very, very large. It's 45%. So it's a conservative certificate. Here, for instance, it was much more accurate. So this tells us at least we are trying to get a handle, and in the future we will be able to predict, not just make a prediction, but provide some confidence bounds or some indication of how good this prediction is going to be. This will not be watertight because the theory is not yet there, but at least it's some indication of whether you trust the results or not. So I think I finish well within my time. So what I presented to you is different ways in which AI models have been useful for physics, whether they're neural operators. But the big change now is that we can do it for arbitrary domains. This is through graphs and transformers. We can do it for very complex PDEs, multi-scale, chaotic, and so on. And even one can learn directly from experimental data. I didn't have the time to show you this, but not just in my lab, but from various other places. This is already possible. But the main challenge is that of sample efficiency. You need data. And since there is not enough data out there, you have to leverage whatever data is there. This is where foundation models can be a game changer, and this is what is being developed at scale now. And finally, I also gave you some indication about how you can trust these AI models if you have these certificates for error. So I think with that I'll stop. I covered quite a bit of ground, but yeah, I thought that's a good review in that case. So thank you very much for your attention.
Thank you, Siddhartha. Of course, it gives complete package, right? What is the scientific machine learning to the certification, right? The end-to-end package. It's nicely summarized, right? What's the state of the art as on today, right? So now the session is open for questions.
I have one question. So in the end, you have discussed about diffusion certificates. So is that somewhat related to the likelihood, like a probability that this is my test data given my training data, or is that
yes? Different? This is precisely, you're right, whoever asked me the question is completely right. This is precisely what it does. So what the diffusion model does is that it simply learns the likelihood, right? It simply learns the likelihood. It tells you exactly what is the likelihood that my test data is similar to the training data. So this is precisely, it provides a quantitative number about that. So this you hit the nail on the head. This is precisely what it does. But to compute it is not easy, right? So you have to train a diffusion model to do that.
Thank you, sir.
Okay, great. The second question?
Yeah. Hello, Professor. Thank you for the very insightful talk, especially the foundation models part. It was very insightful. My question is about a major limitation that is widely seen in modeling discontinuous behavior. So we see that both neural networks and neural operators face difficulty in modeling discontinuous behavior. So what are your thoughts on like how to model this better? Are foundation models the way to go, or what can we do?
Yeah, this I don't share this because actually there is no reason why they do badly in discontinuous behavior. So I'll show you an example. I think I had that example somewhere, right? So I'll show you many examples of discontinuous behavior, and this is a classic example, right? So you see that there are these shock waves here, 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 here. There's no issue whatsoever learning them. This is particularly discontinuities in space. There is absolutely no issue. You can learn that. This was one example. I think I have another example of a shock wave somewhere. So here is a shock wave, right? This is this big explosion that happens, and then there's a shock wave. There is no issue in my opinion in learning discontinuities. Means as long as this is a big, if you use it in a physics informed manner, this is different, right? But if you want to learn it from data, this is, even there are some proofs in one of my papers that, for instance, FNO, this can do it in logarithmic complexity. So there's not an issue if you want to do it in a data driven manner. If you want to do it in a physics informed manner, it's a completely different ball game altogether. But data driven, you can see that there are many, and also in the foundation model we have discontinuities everywhere. Look at this, right? So these are highly discontinuous objects. This is not an issue if you do it in a data driven manner.
Great. Any other question? Okay, if not, then let's thank the speaker. Thank you, Siddhartha. So next time.
Thank you, Shashi.
Like to
See you around next time.
Yes.
Ciao. Bye-bye.
Bye-bye. Yeah.
Good afternoon.
Thank you so
Bye.
much.
Bye.